Thanks. It's a delight to be here talking at this meeting. This is a wonderful meeting because it involves developers and users, and it's a great time to talk to each other. And so those of you who are users, be sure to talk to the developers and, as you just heard, tell us of problems, tell us of things you'd like differently, tell us of things that you like as well. All those things are really wonderful to hear. So today what I want to talk about is applying methods that were developed largely in crystallographic context to cryo-em applications. And at the outset, I want to say that I think the things I'm going to talk about are somewhat useful, but I don't want to oversell them. They don't work as well in the cryo-em context as do in the crystallography. And the reason is because in crystallography, we have very accurate measurements of intensities, of amplitudes, of structure factors, whereas in cryo-em, it's going to be different. So there's some application, but it's not going to be exactly the same as in crystallography. So just as a little bit of background, so I come from the Phenix team that has tools for crystallography and cryo-em. There's a complete package for doing cryo-em work, starting after you have a map in cryo-em. And I won't go through all those. I'm just going to talk a little bit about map improvement today and model building, and you'll hear later about some other aspects from other people. And Helen already talked about the similarity between cryo-em maps and crystallographic maps, the fact that they're coming from different sources but look very similar. And what I want to talk about is, very briefly, they look very similar. And then I want to talk about density modification and what it means in crystallography and in cryo-em and how some of the ideas can be applied and how they can't. And ask the question, can we density modify a cryo-em map and make it any way better? So this is actually the same molecule that Helen showed a picture of. This is an X-ray map of GRO-EL. This is a cryo-em map superimposed on it. And you'll see these are extremely similar. They have slightly different conformations in this particular case. And if you look carefully, you'll see that some of the charged side chains, negatively charged side chains, look different in the cryo-em map, but basically, these maps look very similar. Also, cryo-em and X-ray maps fundamentally come from a Fourier transform analysis in both cases. Helen talked a lot about this, so I won't go into detail. But just to remind you that in the cryo-em case, the Fourier transform of one image is a section through the Fourier transform of the molecule. That means you can make a stack of these in effect and recombine them with the inverse Fourier transform to get a picture. In crystallography, somewhat similarly, a diffraction image is more or less, it's a curve, but it's more or less a section through the Fourier transform of the molecule. You only get the amplitudes, of course. If you get phases from some other source, you can combine those to get a picture. So in this crude sense, they're similar. Now, the experimental information about the Fourier coefficients describing the Fourier transform of this picture is quite different in the X-ray and cryo-em situations. Here, these pictures I'm going to show, these dots are trying to represent probabilities. So on the left-hand side, in an X-ray situation, you're going to measure amplitudes relatively accurately, typically on the order of 5–10% of errors in amplitudes, whereas the phases are measured relatively inaccurately, often as much as 50–90 degrees of error. In cryo-em, essentially you have a 2D Fourier, 2D Gaussian distribution with more or less equal distribution, equal uncertainty in the two directions. So the distributions look completely different, and this leads to many differences between the applications in the two cases. So now let me talk about density modification and the things that are really important in density modification. So density modification is all about correlations in real space and in reciprocal space, in Fourier space. So here's the key concept in density modification in like 3 or 4 sentences. So a change in one Fourier coefficient describing a picture changes the density or map value, depending on how we're talking about, changes the map value at all positions in the map. So each Fourier coefficient affects everything. And that means that if you have an error or a change in one Fourier coefficient, if it's an error in one Fourier coefficient, you're going to lead to errors everywhere in the picture, everywhere in the map. And the key concept is those errors are not uncorrelated in different positions. They're very correlated because they're all coming from one change in one coefficient. So density modification turns that around. It says, let's use these correlations that are present in real space to fix the errors in the Fourier coefficients. It says, let's find the change in a Fourier coefficient that improves the density in one place, one physical location in real space. That tends to fix the Fourier coefficient, and that tends to fix the density or map value everywhere in the picture. That's all density modification is. And there's many ways to implement this, but that's the key concept. So we're using correlations in reciprocal space and real space to solve this problem. Okay. Now, so what are the limitations of density modification because of this, of where it's coming from? So density modification works best if errors in unrelated Fourier coefficients are uncorrelated. A little bit of a mouthful there, but we're saying that in this case, it was going to fail if the errors are local in real space. And let me explain that. So suppose we had a picture in which every part of the picture was independently generated and has totally independent errors here, independent errors there. You could make a Fourier transform of this thing, but you could never do density modification on it because the errors here don't know about the errors there. And if you fix the Fourier coefficient because of the errors here, it's not going to do any good for this one over here. So that's key concept. Those errors in real space are not correlated. So this process is only going to work to the extent that the errors are correlated in real space through the Fourier coefficients. Okay, so this is what I just told you. There's another way that it can fail, and that is if the Fourier coefficients have been already modified to introduce correlations between them. So if a map has already been density modified, in crystallography we've all seen this. If you have an already density modified map and you try to density modify that more, you don't get anything more out of it. And that's because there have already been correlations introduced in real space to make the Fourier coefficients match. So those two caveats there are limitations, and actually they apply in this cryo-em context because to a certain extent cryo-em Fourier coefficients have been modified, so this whole process doesn't work as well as it would in crystallography. Okay, so with those caveats, let me now say how we might apply crystallographic concepts of density modification to cryo-em. So in crystallography, here's one view of density modification where you have a bad map, and then you identify some region of the map where you think you know what's wrong with that map there. So this has to be part of it. You have to be able to say something about the map that you're going to change. So for example, this isn't a great picture, but let's say that I think that that region that I marked out there really is solvent. And then I'm going to say, okay, let me adjust the Fourier coefficients that describe this map in such a way that they pretty much map the experimental ones, match the experimental ones, but also they make this part of the map look flatter. So I'm going to claim that's going to lead to a better map. And that does work. So then we have a better picture in this picture. That's all we've done, basically. So now we have a great picture. Okay. Now let's split this into two halves, because actually we've done two things here. The first half of it is trying to figure out what change in Fourier coefficients is going to make a flat region here. And the second part is how do you recombine that information with the experimental information that you came in with. So here's the first half of that. In the picture on the left, let's make Fourier coefficients from that, and then let's try to find one by one new values for our Fourier coefficients. How are we going to do it? We're going to separate out one Fourier coefficient from all the others. And we're going to take all the others and draw a picture with that. And then we're going to say, how do we adjust this one Fourier coefficient in the context of these others so as to make a flat solvent as much as possible? That process gives us a new value of our one Fourier coefficient. And that process can be exactly the same for cryo-em and X-ray. This step is exactly the same thing. We have a Fourier picture, we take out a Fourier coefficient, we figure out what the change in that will make a flatter solvent. You can always do that. Okay, the second step is, okay, now you have that new estimate of a Fourier coefficient. How do you combine that information with the original? So this is different. So in the X-ray context, you have our distribution that I showed you before, where you know a lot about the amplitude and not so much about the phase. You have some new knowledge that's coming from the map information, from the consistency of our Fourier coefficients that we already had, the one Fourier coefficient, how does it fit in to make this solvent flat? So we have some new information. We merge that information in to get a new distribution. And the new distribution, once again, looks fairly complicated. In cryo-em, it's a little bit different because the original distribution was just a 2D Gaussian. The information coming from the map is also basically a 2D Gaussian. And actually, it's easier to combine those two pieces of information. And it produces a new distribution. Once again, that has less information than this one because we had this amplitude information that limits it to a particular circle. So it's going to be less information. There's one big advantage in the cryo-em context. You get to do this twice, or even more depending on how you want to do it. Typically in cryo-em, as part of the reconstruction process, you're going to reconstruct using half of the data and create a map, two sets of maps, two half maps. They're both complete maps. They're half of the data maps, half of the data maps, that basically have more or less independent information in them. It's not perfectly independent, but it's largely so. And this is a huge advantage in that then you can compare those two maps and ask, what are the differences between them? That gives you uncertainties as a function of position and as a function of resolution in the Fourier transform. That information can be used in this process of reconstruction here, whereas in crystallography, that's much more limited. So that's really a big advantage of the cryo-em system, is that you have these half maps that allow you to do that. Okay, so now let's try to turn this into a tool for density modification in cryo-em using this information. So here's the assumptions that we're going to use in an error model that allows us to calculate numbers here. And so one assumption is that the half maps that I just described are independent, and there are limitations on that, but it's not bad. The second one is that we're going to take these half maps, and each half map we're going to density modify it in the way, the first halfway that I described, to get map-based phases. And we're not going to assume that the results of those are totally independent. And the reason we're not going to assume that is because in the process of density modification, there's a masking effect because you're flattening the solvent. Masking effects introduce correlations in a reciprocal space. So we don't assume that they're totally independent, and we allow them to be correlated. Okay, and then suppose we had such an error model, we might be able to combine experimental and map-based information in a sensible way, and we could predict how good the map is so that we know whether we're getting somewhere. This is all described in a preprint that's online. I want to just mention there's a little bug in that preprint, and just so that if you go through it, you'll know that we're going to fix that. There's a small typo, and it doesn't affect the final results very much. The things I'm going to show you have this fixed. Okay, so now let's test out density modification in cryo-em. And we need a test bed to do this where we basically know the answer. So Wachu, I think, was here and is colleagues collected a bunch of data sets on apoferritin, which is like kind of the favorite, one of the couple favorite structures for doing cryo-em. And he collected a lot of images, and they subdivided into, like, here's a small subset of the images that lead to a structure at about 3 angstroms. Here's one that gives 2.3 angstroms. Here's one that gives 1.8 or 2 angstroms. So basically, if you use all the images, you get a very accurate map, and you get very accurate Fourier transform of that map. And so these pictures here are Fourier shell correlation pictures. So as a function of inverse resolution, so right hand, as you go to the right, it's high resolution. And as you go up, it's high correlation. In this case, this particular picture is correlation between the 2 half maps, the Fourier transform of the 2 half maps. The correlation is a function of resolution. And the high resolution apoferritin map in orange has very high correlation between the 2 half maps up to a very high resolution here on the order of 2 angstroms or so. And the lower resolution map basically is just using some of the images, it falls off. So what I'm going to assume is that in this region where the low resolution map is not that good, the high resolution map is extremely accurate. So we'll use this one as the ideal to compare it. Okay, so now let's take these half maps for the apoferritin low resolution picture. We're going to density modify them, and we're going to end up with 4 maps. These 2 original half maps, and we'll have 2 density modified map phasing half maps, and then we're going to use the little error model I just described to combine those 4 maps into one picture. And then we're going to do a Fourier transform of that and analyze the result as a function of resolution. So now this picture, this y-axis is going to be Fourier correlation of some aspect of what I'm just describing to the high resolution map. So this is like how good it really is as a function of resolution. And so look first at the orange circles, and the orange circles in this picture. This is the estimate of how good the half maps are just by their correlation to themselves. So from the correlation to themselves, we can apply the same formula we use in crystallography to get CC star to estimate the actual quality of this map relative to a perfect one. Those are the orange dots. The blue line that goes with it is the Fourier shell correlation between that average map of the average half maps and the high resolution map. So this is how good it really is. And so they match pretty closely. Next, let's look at the triangles. That's the estimate of how good, as a function of resolution, how good the Fourier coefficients are. And the green line is how good those Fourier coefficients really are by measurement, by comparison to that high resolution map. And once again, they agree, not perfectly, but more or less. And what you may notice is there's a little offset between those 2 things, and that's kind of how much better the resolution effectively is in one case than the other. The word resolution is really complicated in cryo-em, so I hesitate to use it in that way. But basically, you can interpret this to mean that as a function of resolution, the Fourier coefficients are more accurate after doing this process than beforehand. There are many caveats to this, including the masking effect that I talked about before. Okay, so now what does it look like? And that's what really counts. This is also very complicated. It is very difficult to show a totally non-biased picture of 2 cryo-em maps and say this one's better than that one. I'm trying to do the best I can, and I'll show you 2 ways to do this. But the reason it's very difficult is because of sharpening. Because you can sharpen a map and you can make it look a lot different than unsharpened. But that's not very much new information. That's a few coefficients as a function of resolution. What we're really interested in here is are these maps showing fundamentally new information? So that's the hard thing. And so here's one way to do that, is we're going to sharpen the 2 sets of maps we want to compare in the exact same way, in the same process. In this case, we're using the model. It's a high resolution model for each, and the same model for each. So here are 2 pictures. They look fairly similar, but if you look carefully, you'll see that the density modified map has high resolution features that are not present in the original map. And in this particular case, there is no way that you can make those features appear in the original map. At least I have not been able to make them appear. So we talked a little bit earlier about like hypothesis testing. In this process, I have spent so much time trying to hypothesis test, trying to cancel out the effects that I'm seeing. And sometimes they do go away. This kind of thing is really important to try to be very careful to see what happened, what is a real change and what is not. And it is very difficult, I'm telling you. Okay, so these things don't go away. We can look at this another way, and here's another way to sharpen, to try to make things as fair a comparison as possible. We have a tool in Phenix that allows you to take one map and another map and to adjust the resolution dependence of this map, all the Fourier coefficients, so they're identical to the resolution dependence of that map. So we can take our density modified map and make it as good as you want. And then you can take some other map and then you can adjust the resolution dependence to be exactly the same. And then you can ask if they're different or the same. And once again here, there's a lot of things that are much better in the density modified map than the original map, but there's not everything is better. And not every map gets better, many do. And also, as Helen mentioned, different parts of different maps can be very different in resolution. So this whole process that I'm describing of trying to match maps, if you want to be very careful and see if something is really happening, you really have to cut out the local region you're interested in, match the resolution dependence of this one and that one, and now you can tell if they're the same or different. It's very, there's a lot to it. Here's a lower resolution structure where the density modification makes a huge difference as well. Okay, so bottom line on density modification is cryo-em and X-ray maps look quite similar. Their experimental uncertainties are very different. Density modification can be applied to a map in certain circumstances, particularly if Fourier coefficients are not highly correlated. And yes, you can density modify a cryo-em map, and it can be improved. It's not nearly as dramatic as for X-ray. Okay, so somebody, can you give me my timing? Another? About 5. Yeah, okay, fine. So, okay, so now let's talk briefly about model building and then about putting model building together with density modification. So model building, we have lots of different tools in Phenix as well as in CCP4 for model building. Let me just very briefly describe a new tool for model building into cryo-em maps that basically makes use of the low resolution, high connectivity character of many cryo-em maps, which is what you're looking at right here. So the basic idea for this model building tool is let's isolate the density for a particular chain, identify C alpha, C beta positions from where there are bumps, and appropriate distances between them, construct and refine all that model. And this works pretty well. And just jump to the bottom line on this. So here's a relatively low resolution map that can be built about 80%. And looking in closely, you'll see that there's some things that are right about this, there's some things that are wrong. If you look in detail, this alpha helix is mistraced in this little particular region here, right? So that's the kind of mistake that may be made at lower resolution. At high resolution, so here's a 2.6 angstrom map. Oops, sorry. Can build much more models. They're pretty good. As Eleanor said, none of these automatic tools for model building finish it off for you. They're a tool to get you close to the right answer, and then after that, your job is to finish it off. And one of the things that you, as mostly crystallographers, are very good at is this last final stage. And actually, the cryo-em crowd is just learning that you don't get the final answer from the software. They actually want to have the whole thing all completely done and ready to deposit. And you guys are like into this last step, which is, I think, great. And that's the way it has to be. Okay, so there's lots of maps one could use for model building. So your question in your mind may be, okay, can we use these density modified maps? And then actually I want to go a little bit further and say, can we do any iteration of the model building and density modification? And so very briefly, yes, we can do this, but with many caveats and many things that you have to be careful about. So just first off, suppose we took a regularly sharpened cryo-em map or a density modified map. Does it make any difference in model building? So we have a bunch of model building cases from using data from the EMDB. And this shows the fraction of correctly built residues. In each dot is x-axis is what fraction is correctly built with half map sharpening. The y-axis is how many are correctly built with density modified. And it's not a huge difference. The density modified ones are a little bit better on average, but some are better, some are worse. Bottom line is it does make a difference. And so at this level, sure, you may want to try it both ways, and maybe you'll get more built one way or another. You can actually go one more step, and this one, I'm going to make you nervous with this one already, I know, because we're going to use the models, but in cryo-em, we don't have something that's very important that we have in X-ray. So in X-ray, when you build a model and you use the model to generate a map, you have Randy's tools and others that basically give you a relatively unbiased picture from that model. It removes some of the model bias. In cryo-em, you fundamentally can't do that. So there's no 2FO minus FC, there's no M2FO minus DFC map in cryo-em, and you can't make it. So all maps will be biased. And we're going to try to get around that by building a lot of models and using the diversity in the models to give us some error estimates. But this is not going to remove all the model bias. It's going to give you a source of information, and that source of information is also going to be correlated with our initial map. So there's all the risks in that. So in any event, we can do that. So we're going to build models. We're going to density modify, build models, use the model information in density modification, make a new map, etc. And what do we get? So here's our apoferritin map at 3.1 angstroms. Here's the density modified version. It's a little bit better. Here's after carrying out density modification with the model-based information, it's a lot better map. And you can compare that much improved map to the high-resolution map that's truncated at the same resolution and is very similar. So we've gone from this to that. And so I wanted just to think about that. Okay, this is definitely improved. There's no question about it. But yes, it does have model bias. So if for example, in your sequence, you had the wrong side chains, that would show up here. So you can't use this as an absolute answer, but it is useful in iterative processes of improving things. So here's another one, at lower resolution, improving the map. Here's one, beta-galactosidase. These three areas, you'll see gets a little sharper. This thing actually goes away. So it doesn't do everything, but the map is more interpretable in many cases after this density modification with the models. And also notice that this beta-galactosidase at low resolution, it doesn't get real sharp. It doesn't look like the model like that high-resolution one did. Why doesn't it? It's because the 3.1 angstrom map defined where the model would be built. And then the high-resolution information is coming from the fact that only certain shapes of molecules fit into this density, and therefore you get more information out of it. This one, at low resolution, you don't know where to build it. Everything is averaged out, and since we built multiple models, it doesn't look like a sharp model at all. It looks like that's how much information we got by the multiple model building. So the multiple models is totally crucial here, and they have to be relatively independent for this all to work. You can also build more by doing this. So initial model build, this one is not built that much, 36%, and then 46% after the density modification. Also, the maps do get better. Now, for beta-galactosidase, we have a high-resolution map, so we can compare the Fourier coefficients to the right answer as a function of resolution, just as I showed you before. And here, so the blue is the initial map, and then the other colors are after density modification with model. So not so much more after density modification, but each cycle is a little bit better. Okay, so summarizing, what should you take away in terms of what you want to do, given what I've told you today? So if you have cryo-em map, I say, yes, go ahead and density modify this map. And it may give you an improved map. Look carefully at it to see if it's really improved or if it's just sharpened more, which can be confusing. Not confusing, can be deceiving sometimes. And you should be, the kind of thing you might expect is 0.1 to 0.3 angstroms of resolution change, effectively, that kind of number. And it works best if you have half maps that have relatively uniform noise. If these half maps have been very strongly masked, indirectly or directly, so that the solvent is very, very flat, you won't get very much out of it. Go ahead and try model building. The tools we have and the CCP4 tools for cryo-em model building are getting pretty good. And in the 3 to 3.5 angstrom resolution range, they work really very, very nicely. Sure, go ahead and try the model-based density modification. It's available in Phenix in the command line. It takes a long time because you're building a lot of models and you're averaging everything in. And take it with a grain of salt about what you can and cannot infer from the information. The models are not totally independent of the map, so they can reinforce errors. So if the map shows a side chain in the wrong place, then the models are going to get built there, and then you can iterate that process, and you're going to build all the models in that place. So if there's something wrong about the starting map, that will get amplified. And model bias, as I said, cannot be prevented if you're using models, but the multiple model idea allows you to reduce the problem of that. Okay, and I want to thank all the Phenix team for all the help in putting all this together, and thank you for your attention.
So there's already a question from Randy at the front.
Randy, you're not allowed to ask questions.
Yes, I am. So in this multiple model building, using multiple models to get around the problem of model bias, could you do something like an omit map where you build multiple models omitting different volumes and then stitching together those volumes from the modified phases?
Yeah, so so this is a great question, Randy. And actually, there's something implicit in this question, which is how much does building a model or having an accurate map in one place improve the density in another place? And the answer is, in my experience with the cryo-em, only a little. So not nearly as much as for crystallography. So I have tried what you have said, and it's not useful yet. So it may be useful at some point in the future, but you can't do that right at the moment. Yes. And however, a caveat on that, if you have a very accurate model, like so in the apoferritin case, you come in with the high resolution model and you use that as from one place, that does help the density. So if you get good enough, then it could happen. And so maybe if the method's just a little bit better, then that would work. Yes.
Okay, we have a question here and then one right up at the back.
Can you comment on the resolution range that density modification is most useful? So is it most useful at the one you said, or can it be useful at lower resolutions?
So it seems to be, I've only tested in the range of 2 to 4.5. That's my entire testing set. And it seems actually in the lower resolution to work better than the higher resolution range so far. But I haven't been able to figure out, like, this is the thing about your map that's going to determine for sure whether it's going to work. I don't know the answer to that yet. Resolution by itself is not going to be it. And software program used to generate the map, that's not it by itself. So I don't know, exactly.
Hi, Tom. Very nice. Question about this, I think you said about independence of observation. So if you take half data sets from cryo-em, you can assume they're somewhat independent. What's the reason for that? But the actual question is, what would you have to do to crystallographic data to generate independence? So for instance, if I had 50 data sets measured crystallographically and I kind of averaged them because I got various resolutions and I did this twice, would I have more independent average observations than I would from a single data set?
Yeah. So that's a very interesting question, Frank. The basic answer is you're not going to get to do this with crystallography. And the basic reason is, so you could do 2 data sets for crystallography, and you could say these have independent errors. It's true, you could have independent measurement errors in those 2 cases. But actually in crystallography, the important thing is not the experimental errors in general. It's the fact that the model is wrong. It's the fact that your model is very poor, and so you have very poor phasing. So it's a model problem in crystallography. In cryo-em, you have independent half maps where the experimental errors are more or less independent. And in fact, that is where the problem is in cryo-em. So that if you took many more measurements of cryo-em data, you will get a much better map. Coming back to crystallography, if you measure your data more and more accurately, you're still not going to get a better map. It's going to be marginally better because the problem is not in the amplitudes. The problem is getting the right phases. I'm not sure if I made that completely clear, but fundamentally it's different in crystallography where the errors are compared to cryo-em. You can do the half map thing in cryo-em. In X-ray, taking multiple crystals doesn't do you any good in this context. A tiny improvement.
Okay, we have another question over here from Randy.
Great talk, Tom. You starting from half maps, do you see ways to go to your independent data, which are your particles? Often it's a very subjective selection of the particles. Most particles are thrown away. Can you now go to your multiple model, refined models, and sort out the original particles and make more omit particle sets?
Yes, in principle, one could do, those kind of things will be much more powerful than what I'm talking about. Actually, I talked with George about these things, and he mentioned that in his software, he's actually put in a hook that you can take external software like this, carry out operations on maps at early stages of processing, and include that in the iteration process. So actually, it's possible to do what I'm describing and what you're saying, a part of that already. In terms of the actual particle picking, that would be another level of integration. But I think it's a great idea. And yes, fundamentally, going from model-based information all the way back to the beginning in cryo-em and trying to do it in a very careful way that doesn't bias things, I think is a very powerful and it's a great idea, yes.
Okay, so in the interest of time, I think we should maybe move on.
I'm happy to sacrifice a bit of my time, if I may ask a question to
sure.
Yes, so you were just mentioning bias, and that would surely be a concern. What do you think people should deposit if they use density modified maps? And are the maps that you were showing deposited?
It's a really great question. So actually, I think the answer is going to be, for cryo-em, be sure to deposit something that is as close to the original, like you deposit your images somewhere. Okay, so then that's already there. Okay, and then second, when you create maps, deposit the very first map. If you do a processing program and it's going to give you a map, deposit that map, not mask, not sharpen, just deposit that thing. So then now we have the next stage. Okay, and then maybe you sharpen that map, and if that's the map you really use, deposit that one too. And then if you density modify that map, deposit that one too. And if you do iterative density modification, deposit that map. But I put a star on that last one because the real purpose of this iterative process that I described is to get a map so that you can build a model. And then you want to take that final model and you want to interpret it against, maybe the density modify is pretty safe because that's not going to change things in a fundamental way with any bias. You could check it against that, but check it against the original map. That's where the information really is, and that's not going to change. And you can look, you can sharpen and unsharpen that one, so you can look as a function of resolution. That's where you want to do all your final checking, is against that original map.
So, and the maps that you were showing in your talk, are they deposited or available?
I have not deposited these maps yet. I will put them online, and yeah, so that's a good idea. I will do that.
Great. So can thank Tom once again, and Isabel will now get set up.